Hello, my name is Giancarlo Mafiol, part of Team 18 for Modeling Control of Robots, and we're going to be presenting projects 1 and 2, which is the synthesis of a 4-bar mechanism, and later on, the kinematics of a slider crank mechanism. The problem statement for the 4-bar is we were given a set of coordinates for 2 points along the coupler link, for which the mechanism was responsible to go through in sequence. You can see a basic layout of the mechanism, what it looks like the 2 points are responsible for, and the 3 positions it's got to transition through in sequence. And to help guide you through the synthesis, Yojans.
Thank you, Giancarlo. So what we have here is the 2 basic equations that we used to calculate the poles. And once we had the location of the poles along with the location of the endpoints of the coupler link, we were able to calculate the length of each link. Here is the mathematical walkthrough for those calculations. Here we have pole A, pole B, using the inputs from the endpoints of the coupler link. For both A and B, we calculated the X and Y coordinates of pole A and pole B. Using all those coordinates, we were able to calculate the length of each link. These values were relatively close to their smaller or higher values, so we ended up rounding off to these values that you can see here, so that we could avoid compounding error in the remaining calculations. Theta 1 was set equal to 0 because the y-axis was 0 for both poles A and B. And then what we did is we used theta 2 between 1 and 360 degrees. Using these equations that you see here on the right to calculate theta 4 and theta 3, because there were 2 possible solutions for each, we ended up with 2 different closures of the mechanism. And as you can see here, these are the 2 closures, the 3 positions for each closure of the coupler link, and the endpoints, the motion of the endpoints passing through each of those positions. And here's Giancarlo to walk you through the animation.
And here you can see this is an animation of the motion as rendered in SolidWorks. I'll verify the information gathered in MATLAB. You can see the mechanism transitioning through all 3 points in sequence. And these arcs actually trace out the paths of points A and B along the coupler. These type of 4-bar mechanisms have a wide range of applications, from the real mundane and everyday objects like vice grips and windshield wiper linkages, all the way to the more bizarre, such as activators for electronic switches or relays, and even to go so far as locking mechanisms for the seats in roller coaster and amusement park rides. Next, I'll guide you through the kinematics for the slider crank mechanism. Is Jose.
The problem statement for the slider crank mechanism was that given a set of specifications, we had to plot the entire position analysis using these values. We also have an extension arm that goes from point 3 out of 15 inches at an angle of 30 degrees relative to bar 3. We did this in 1 degree increments of theta 2 as our input value, and we plotted this entire range, and we also set up a model of it in SolidWorks. This is R2, this would be R3. Your R1 would be the sliding length, and R4 would be the height. And this over here would be the QS that we added. These are the equations for the position analysis. All of these values were found using the input values of theta 2 that we had originally. After we found all of these positions for theta 3 and R1, we were then able to find omega 2 using that information and the R dot that was provided in the specifications. The same thing was followed for omega 3, as well as alpha 2 and alpha 3. Applications for our mechanism in particular can range anywhere from windshield wipers to a production line mover. The fact that the arm drops at a relatively low rate allows for ease of placement of an object on a ramp. And the more practical and common use of this slider crank is in an internal combustion engine, where the crank itself is the crankshaft and the slider is the actual piston. And that's it.
Okay. Good and bad.
4 minutes.
4:45.
Hour 5.
4:45. That's almost 5, man.